So we can start with question 11 over here, where we have 9 players. We want to split them onto 3 teams such that the tallest players are all on 3 different teams. So we do first is that we see the number of total ways, which is 9 choose 3, times 6 choose 3, times 3 choose 3. Now we want to see the number of ways that we can assign the tallest player and the other 6 players, the 6 remaining players. So firstly, for the first team, we have 6 choose 2, and that's the way to assign those 2 people. So then we have 6 choose 2, 6 choose 2, times 4 choose 2, times 2 choose 2. However, it does matter what order they're on, as in if we have these different teams and then we assign the different first player, if we assign the 2 players to a different team, it'll be a different team in totals. Then we have to multiply this by the number of permutations. So we multiply this by 3 factorial. And then this overall ends up becoming 15 times 6 over 84 times 20. And that ends up simplifying to 9 over 28, which is C. Now we can move on to the next question. And we have, what we first notice is that we have a 60-degree arc. So when we think of a 60-degree arc, we can try to draw this by insert, draw. So first we'll draw what it'll look like fully extended. And this is the 60-degree angle. I'll try to make this. So this is our arc. So that's the extended version of our arc. Now we want to see what this length will be. So we draw this arc. And we know that this is 60 degrees. We have 60 degrees. This is 60 degrees. So what we do with this information is that since this is 60 degrees, this is 3, then this also has to be 3 because it's an equilateral triangle and it's because we know it's isosceles. So we want to see what the total length of the curvature will be because we know that it goes from here to here. We'll let this be C prime, and D prime. And we know that this varies as this will end up going higher and this will also end up going higher. It'll form a little curve like this, which will be the same length here. So what we can do is that we can draw a dotted line here and draw a dotted line here. And since we know that these two are the same area, we can transform this into our rectangle with a side length of 3, because we know that this value is 3, and we know that the length of the windshield wiper is 3.5. So we have 3 times 3.5, which gives us C, 10.5. Now we can move on to question 13. Since we know that it's 6 sectors of 6 different sizes, we can, without loss of generality, let the order matter. So then it'll be 1, 2, 3, 4, 5, 6, where the first is the largest sector and the last is the smallest sector. So what we do first here is that we want to see how many different ways we can assign different colors, making sure that these conditions are satisfied. So what we do first is that we, without loss of generality, let the first one be painted red. So we have red, and then we have 3 different cases. We have 4 different cases here. One where 2 is blue, and then that means that's, and then one where 2 is green. And then that also gives us a couple different cases for the next one. We can also look, since this is 1 and this is 2, we know that 1 is connected to 2, but it's also connected to 6. So we have 2 different cases there too, where it's blue and where it's green on the other side, on number 6. So first of all, looking at the red, blue, and then 6's blue case, we have 2 greens and 1 red to fit the spot of 3 thingies. So since we have 3 and we know that the 2 greens cannot be touched and we only have one way, green, red, green. And then we can do the same thing with red, green. And then if it's red, blue, green, then we have to see how many ways we can put red, blue, green, and then in the spot so that the first one is not blue and the last one is not green. So then there are a total of 6 ways to arrange red, blue, green, and then there are 3 ways that do not satisfy those conditions. Then we have 3 ways with red, blue, green. And then we can do the same thing there and we get 4 ways for that. So we have 4 times 4. We have 4 plus 4, which is 8. We have 8 ways if the first color is red. Now, if the first color is blue, then we have another 8 ways, and if the first color is green, we have another 8 ways, giving us D, 24. Moving on to question 14, what we have is that the first 3 integers, their average is 2025. The first 4 integers have an average of 2024, and the first n integers have an average that is like 2028 minus n. So we can work with this, letting Sn be the sum of the current terms. So given Sn is the sum of the current terms, how we can work is we know that S of 3 is 2025 times 3. And we know that S of 4 is 2024 times 4. And we can go on letting S of n equals 2028 8 minus n times n. And we know that this will always satisfy the conditions, as it'll be the first n terms, and the average will always be 1 less. So we can get that S of 1 is 2027. If we plug, since we know we can determine our own sequence, we have S of 1 equals 2027 from this. We have S of 2 equals, wait, no, never mind. But what we can do is that we know that X of n is S of n minus S of n minus 1, right? Because S of n minus 1 plus xn is S of n, because S of n is the sum all the way to the nth term. So if we add in the n plus 1 term, we get the sum all the way to the n plus 1 term. So expanding this, we have x of n. I'm just going to type this out. We have xn equals 2028n minus n squared minus 2029 minus n times n minus 1 equals 2028n minus n squared plus 2029 minus 2030n minus n squared plus n squared, which simplifies to negative 2n plus 2029. And since we know that every number in the sequence has to be a positive integer, we have negative 2n plus 2029 bigger than 0, so the maximum n equals 1014, which gives us B. And now we can move on to question 15. We know that a container has a 1x1 square bottom, a 3x3 open square top, and 4 congruent trapezoidal sides. So what we can do is that we know that since it takes 35 minutes to fill the container up to the midline of the trapezoids, using the diagram they give, so we can first draw the trapezoids. we can use we can draw the trapezoids. And we know that the top has a side length of 1 and the bottom has a side length of 3. So then we know that the midline, its length must have a length of 2. So what we do is that we know that it scales, and since it's a 3D object, it scales by a factor of, it cubes it. So we go from 1, going from 1 to 8 to 27. And that's like the volume that is like using the cubic. So we know that it takes 35 minutes to go from 1 to 8. And we know it takes 19. So then we know to go from, we have 35 over 8 minus 1 equals x over 27 minus 8, because we want to get it all the way up to 27. So solving this, we have x equals 95, which is our answer. So for this question, we first translate 25 minutes into hours and minutes, which gives us 33 hours and 45 minutes. Since it's a 24-hour clock, we have 9 hours and 45 minutes. So what we do with this is that we want to find the angle between the two clock hands. We know that if we draw our circle, we know that our minute hand has to be exactly at the 45. But our hour hand will be slightly past the 45. But we want to figure out what that angle is. So what we do with this is that we know that for every 60 minutes, the hour hand moves 30 degrees because it moves 60 because it moves 12 times. So every 60 minutes it moves 30 degrees. So since every 60 minutes it moves 30 degrees, we have 45 over 60 equals x over 30. So we know that the angle must be 22.5 degrees. So we want tangent of 22.5 degrees. We let tangent of that equals x. And that we let that equals x. So we can use the tangent double angle formula to get tan of 45 degrees. Tan of 45 degrees. Insert equation. We have tan of 45 equals, and then using the equation, we have 2x over 1 minus x squared. 2x over 1 minus x squared. So we know that the tangent of 45 degrees is 1 using our 45, 45, 90 triangle. That means that 1 minus x squared equals 2x. And thus, x squared plus 2x minus 1 equals 0. And solving that equation, we get x equals square root of 2 minus 1, which is b. So we can move on to the next question. Let me just add some more space. So moving on to the next question, we have each of the 9 squares in a 3x3 grid is to be colored red, blue, or yellow in such a way that each red square shares an edge with at least one blue square, each blue square shares an edge with at least one yellow square, and each yellow square shares an edge with at least one red square. Colorings that can be obtained from other rotations or reflections are considered the same. So what we do is first we make a grid. We can use a table. So we can first let the center of that be red. Without loss of generality, let it be red so that we can rotate colors and then we can multiply by our answer by 3 at the end. So we know that at least one of these has to be blue. So we can, without loss of generality, let this be blue because we can rotate it and then see if anything changes. If this must be blue, we know the blue must be touching at least one yellow square. So we have one scenario where this is yellow, and if that is yellow, then this must be blue. And if that is, wait, no, since that is yellow, that must be red. And this is blue. We can either let this be, so this is one scenario, and then red, blue, blue, yellow, red, blue. No. But we can mess around and try to find a couple colorings. So instead of doing that, we can continue working in a clockwise direction. So since each red must touch a blue, each blue must touch yellow, each yellow must touch a red, this red must touch a blue. This blue must touch yellow. And continuing, we have this scenario where this yellow is already touching a red. So we kind of have choices for these. There are a couple scenarios for this one. So we can start with setting this to red. If this is red, then this must be blue. And if this is blue, then this must be yellow. However, if this is yellow, there is no red to satisfy that, so that scenario can't work. However, we can try using yellow here. If this is yellow, this must touch a red. And if this is red, this must touch blue, and this works. And if we use blue here, this blue, it must touch yellow, but it's already touching yellow. So there are, if this is a red, then this can be a yellow, or this could be another red. However, if the bottom one is yellow, then we can get that this can be either this has to be a red, and this could be a blue. So we know that this doesn't work. So we should have 4 cases depending when this is a blue, as this can be a red, blue, red, blue, red, red, blue, red, yellow, or it could be a blue, yellow, yellow, blue, yellow, blue, yellow, blue, or blue, yellow, red. So that gives us 4 cases, and that's if the center is a red. So we have 4 times 3, it gives us 12. So that gives us C. Now we can try this problem. So what we do is that he has a probability of winning of 1 over 3. So we can define a couple of states. Our first state is that the state where he is in 0 tails, 0 heads, 0 tails, or 0 wins, 0 losses. 0 losses. So the expected number of games required when he is in 0 wins and 0 losses is 1 plus the amount of games required for him to be when he's at 1 win, 0 losses, plus the amount of wins when he's at 0 wins, 1 loss. And then since there's a 1 in 3 chance that he'll win, it's 1 over 3, and this is 2 over 3. We can do the same thing with 1 win, 0 losses, where it's 1 win, 0 loss, and then there's it'll always be plus 1 because it's 1 more than the previous case. Then it's 1 because we're rolling again. Then there's a 1 in 3 chance that it'll still stay 1 win, 0 losses. And then that's it. And then we also know that if it's at 0, and then also there's chance 2/3 chance that we'll win, but then we won't add any games, so we don't have to worry about that. Then we have 0 wins, 1 loss, and that's 1 plus 2/3, 0 wins, 1 loss. So then, since we have this equation is centered around, this only has one variable and this only has one variable, we have the expected values of games, number of games for 1 win, 0 loss, equals 2/3, equals 3/2, and then expected value of 0 wins, 1 loss is 3. That's the that's expected value. So then we can plug this back into our original equation to get 1 plus 1/2 plus 2, which gives us 7/2d. This is a really fun problem. So what we do is that we let C be the column number and R be the row number. So if it's in the first scenario where he puts a 1 through 99 from left to right, then we have 91 times C minus 1. We have 91 times C minus 1 plus R. And then that's when it's in the column form. It's all when we do in the row form, we have 141 times R minus 1 plus C. And we want these to be equal, as they'll have the same number in both scenarios. So we have 91 times C minus 1 plus R equals 141 R minus 1 plus C. So that gives us 140 R minus 141 equals 90C minus 91. So we have 14R minus 9C equals 5. And we want to find all values of these that work as long as R is less than 141 and C is equal to and C is less than 91. So we know that R equals 1, C equals 1 works. And since this is and then we also know that since this is the top left where it's 1, we also know at the bottom right that is also equal at when C is 140 and when it's at 141.91, that also works. Or 91.141, sorry. 91.141 also fits those conditions. So we use that, and what that ends up giving us is that R equals 91, C equals 141, and we can see how many solutions. So if R increases by 9 and C increases by 14, that'll still satisfy the equation. So we have R equals 1, C equals 1. We have R equals 10, C equals 15, and we can go on like that and bash out all that numbers, and we'll get that that there are 11 solutions, and that gives us C. Moving on to our final question, question 20. We can do similar to what we did with question 18. We can define a couple states. So we can say that the odds that it wins at when it's at point 0 is E of 0, and then that is 1/2 E of 1. Then we also have E of 1 equals 1/4 E of 2 plus 1/4 E of 0. We also have we can continue doing that with E of 2 equals 1/4 E of 3 plus 1/4 E of 1. E of 3 equals 1/4 E of 4. But since we know that we're trying to see what the odds are you can get to E of 4, we just have 1/4 plus 1/4 E of 2. We can then work our way through these equations and solve for them, giving 3 equals 1 over 4 plus 1. We have E of 2. We can substitute the equation for E of 3 into E of 2, giving us E of 2 equals 1 over 4 plus 1 over 4 E2 plus 1 over 4 E of 1, which simplifies to 1 over 16 plus 1, we have 15 over 16 E of 2 equals 1 over 16 plus 1 over 4 E of 1. Now we can plug this into equation number 1, giving us 15, or we can say that E of 2 equals, multiplying each side by 16 over 15, we have 1 over 15 plus 4 over 15 E of 1. Plugging that in, we have E of 1 equals 1 over 60 plus 1 over 15 E of 1 plus 1 over 8 E of 1, which ends up giving us E over 120. We have 97 over 120 E of 1 equals 1 over 60. So then we have E of 1 equals 2 over 97, meaning that E of 0 equals 1 over 97. And since we're looking for the odds that it reaches 4 from 0, we have E, 1 over 97. And that'll be it.